Okay, so thank you very much, everyone, and thanks for inviting me to give the keynote presentation at QSC 2020. I hope maybe next year we will be able to see each other face to face, but it's also exciting to have an opportunity via Zoom to share with you my point of view on software engineering for quantum computing and quantum computing for software engineering. Just a quick comment about myself. I lead research at JPMorgan Chase, so I'm the lead of research and the head of research and engineering at JPMorgan Chase. I started this job just in January of 2020, so 6 months ago. Before, I was a distinguished research staff member and a senior manager at the IBM Watson Research Lab in Yorktown Heights, New York, and was responsible for the project for quantum algorithms and applications. So my team and I created at IBM, we created the algorithms and applications layer of the Qiskit software stack. I was actually responsible for Qiskit Aqua. I was the head of the project and the approver of the pull requests and so on. So that experience, coupled with the experience that I have now at JPMorgan Chase as the head of quantum computing, I think puts me in a position in which I can share my experience with you on the software engineering challenges and opportunities that quantum computing offers now. So in the first part of this presentation, I would like to describe to you what software engineering can do for quantum computing. And in particular, I would like to say what we should do as a community from a software engineering perspective in quantum computing. What are the opportunities? What are the challenges? And what are the mistakes that we should not make? Now that quantum computing is like a new adventure for many people, we have an opportunity to do things right. So that's what I would like to describe here based on my experience. So first of all, how far are we from the point in which we can actually use quantum computing at an industrial level to have an impact on real problems that can actually change the industry. For example, we know that quantum computing lends itself to any domain in which there are problems with exponential complexity. It doesn't make any sense to use quantum computing for problems that do not have exponential complexity, because classical computers are already doing a very good job there. But for problems with exponential complexity, that's where quantum computing can make a difference. And in this particular slide, I wanted to show you the an example that probably resonates very well with people that have a background in chemistry, or people that work in pharmaceutical companies, for example, companies that are looking for new materials and so on. So here we see a list of molecules on the left and the chemical formula next to the name of the molecules. These are all molecules that we probably deal with on a daily basis, or soon, every now and then we have definitely interacted with them. So like definitely we deal with water and caffeine and sucrose every day. Maybe we take acetaminophen when we have a headache, and penicillin if we have like an infection or something. But so these are basic molecules. Like these are not even like sophisticated molecules, like the ones that a company working in new materials, like new plastics or something like that, or a pharmaceutical company are looking for. So let's look how many classical bits we need to simulate one of these molecules on a classical computer. So for example, for water, we need 10,000 classical bits, which corresponds to 14 qubits. So keep in mind that as everybody knows in this audience, I'm sure the computational power of a quantum computer is exponential on the number of qubits. The 2 to the power of 14 is what we need to simulate water. So for water, we have no problems. We can do that on even on one of today's quantum computers, as well as on any classical computer, because it's not a very expensive computation. But as we move down in this slide, we see that the situation becomes more and more difficult, more and more complex. For example, for the molecule of caffeine, we need the 10 to the power of 48 classical bits. So we need a classical computer with 10 to the power of 48 classical bits. So just to give you an idea, the number of atoms on the planet Earth, on our planet, is 10 to the power of 49. So there is never going to be a classical computer with such a strong computational power that is basically corresponding to 1/10 of the atoms of the planets. On the other hand, if we look at how many qubits we need to simulate caffeine without approximations, it's 160, which is not impossible to conceive right now. We're not at that point yet. For example, companies are now, hardware providers are in the range of between 50 and 60 qubits. So 160 is not that far away. It's not a number that is completely not imaginable at this point. So why do we do this? Because basically, for example, if we look at pharmaceutical companies, as I mentioned before, pharmaceutical companies make up new molecules most of the times. These new molecules are candidates, for example, for new drugs. So the most important thing to make sure is that when somebody puts together some atoms to create a new molecule, is that this molecule stays together. It's stable enough. The bonds between the different atoms are strong enough to keep the molecule together. Now, this requires computing, for example, the ground state molecular energy of the molecule. And this computation is actually factorial on the number of spin orbitals in the molecule. So that's why this complexity comes together in this slide. But you also understand how important this example is, because when pharmaceutical companies are making a new molecule for a new drug, they definitely want to make sure that the molecule stays together, that it binds to the receptor of a protein in the body, and it doesn't have side effects. So these are all properties that need to be simulated with a computer before really testing the drug on animals and eventually human beings. Unfortunately, today's classical computers, they cannot even simulate caffeine, let alone a new drug, say for COVID-19. So what happens is that these drugs are often put together and tested and simulated classically with approximations, which leads unfortunately to side effects, drugs that can actually cause serious problems. So this is just to give you a perspective. But an example that I really liked is also the following one, which comes from the domain of combinatorial optimization. So when you sit 10 people around the table, maybe you, like I know, of course, that the complexity of this problem is factorial on the number of people, but I never stopped for a second to think that 10 factorial is actually 3,628,800. So basically there are 3,628,800 possible ways to sit 10 people around the table. And you may have constraints here, for example, why do I want to put one person next to another one, but not next to somebody else, who should be across the table from another person, and so on. So this is also a problem faced by transportation companies. They need to find the best routes to deliver merchandise and so on. So you see how the complexity grows fast here. Of course, for 10 factorial is nothing for a classical computer today. So that's not the problem. But of course, when the problem becomes more and more complex, the situation, the complexity of the problem may be not affordable by a classical computer. That's where quantum computer can make a difference. So where do we stand right now in the journey of quantum computing? So we all want to go to so let me start from the right. We want to be in the quantum advantage era, in a sense. So quantum advantage means that we have quantum computers that can actually solve industrial size problems. For example, really like a classical problems that classical computers may take a much longer time. I'm not talking about quantum supremacy, but quantum advantage. So for example, you may have so the point in which quantum computing really beats classical computing for industrial size problems. That's what quantum advantage is. So you may have a problem that takes, say, 10 days on, or maybe a month, something like that, on a classical computer, but it may take like a couple of hours or something like that on a quantum computer. We're not there yet. Today's quantum computers don't have enough qubits, and not even if they have like a significant amount of qubits, unfortunately, they are hindered by quantum noise and by short coherence time. So at this point, we in the road to quantum advantage, even though we don't, we're not yet at the point of having achieved the quantum advantage. However, there is a lot that we can do. It's time to do research and to develop new algorithms. And it's also a time in which a lot of companies are doing experiments on quantum computing. But maybe it's also a time in which these experiments can become just more than just a simple experiment. It's almost like transforming science into business for the future. So in the past century and in the first 2 decades of this century, basically there has been a lot of work that has been done from a foundational theoretical perspective towards building quantum computers. But now, as I mentioned, it's time to become quantum ready. So it's time to build the general purpose algorithms, but also to build the domain specific algorithms in all those domains that, as I mentioned before, lend themselves to the power of quantum computing because of the exponential complexity of the problems that they exhibit. Chemistry is definitely an example that I explained before, and optimization is another example that I also showed before with the 10 people sitting around the table as a very trivial example. But in reality, even though quantum computing is inspired by quantum mechanics, really there is no need for the problem being modeled or being solved to have anything to do with physics or chemistry, even though that was, as I said, the original inspiration. So what we can do now is even apply quantum computing to artificial intelligence, finance, and as I will show you towards the end of the presentation, another domain that can be software engineering. So right now I'm talking about software engineering for quantum computing, but then I will describe quantum computing for software engineering, and we will see an example where quantum computing can actually make a difference. So while we become quantum ready, what should we look at? Should we look at the number of qubits that hardware providers are giving us, or should we look at other unit of measures? So researchers have introduced a different unit of measure that is not just the number of qubits. It's called the quantum volume. So truthfully, the number of qubits is not the right unit of measure to assess the computational power of a quantum computer, because many other things have to be taken into account, like the connectivity between the qubits, the hardware gate set, the error of the gates and the decoherence of the gates, the number of parallel operations that can be performed. Basically, we need a unit of measure that takes all these components into account, including the number of qubits. So you see here an example in which on the top, no qubits have been added to a computer. Qubits added 0. However, the error rate has decreased by a factor of 10. In such a situation, for example, the quantum volume increases by a factor of 24. On the other hand, at the bottom, we see another example in which a computer gets nothing less than 100 new qubits. However, the error rate does not decrease at all. And as a result, the quantum volume does not increase at all either. So that's what we need to look at. For example, right now, according to a recent statement made by Honeywell that was in the press a couple of weeks ago, Honeywell has the most powerful computer in the world with a quantum volume of 64. It's the highest quantum volume ever achieved so far. Honeywell has also a roadmap for increasing the quantum volume of its computers by a factor of 10 year after year. So this actually shows that quantum computing is actually going much faster than we all ever thought at the beginning of our journey. For example, when I started working on quantum computing, maybe about 5 years ago, there was this conception, this idea that quantum computing would become efficient and operational at the end of the current decade, so like around 2030. But maybe based on the fast improvement, the fast progress that hardware providers are making, we are now seeing a situation in which quantum computing may actually become useful for industrial size problems and operational and effective much sooner than that. It's very hard to make a prediction, but it's also very important not to sit around and wait for the moment to happen, because when that moment arrives, when quantum computing becomes fully operational, at that point, all the companies who have invested in quantum computing and have created knowledge inside their own companies and have created also a portfolio of algorithms and applications, those companies will be able to survive. But the companies that have not invested significantly, don't have knowledge inside themselves, don't have assets like new algorithms and applications, will face some kind of extinction event, similar to like the death of the dinosaurs. Like many companies may actually be left behind, because at that point there will be a dramatic advantage for all the companies that have the power to use quantum computing and have the ability to solve complex problems in real time. And this applies to pharmaceutical companies, companies that work with chemistry in general. It also applies with anything that uses AI. So it's actually AI is a domain that is used everywhere. It applies to financial company like the company I work for, JPMorgan Chase, because financial problems do have, many financial problems do have exponential complexity. So even financial institutions need to be ready to solve those problems using quantum computing. That's why I work for JPMorgan Chase now. So that's the excitement about quantum computing. But at the same time, this also means that while we do this work, like the new construction of new algorithms and new applications, we need to do it right. We need to do it with software engineering principles in mind. So first of all, I wanted to show you this quantum computing stack. I think many people don't realize maybe how complex the quantum computing stack is, and also how diverse it is. So I remember many times I heard people say like, oh, I cannot work on quantum computing because I don't have a PhD in physics or something like that. Like, well, I don't have a PhD in physics myself. I have a PhD in mathematics. I have a lot of colleagues working on quantum computing with a PhD in chemistry, a PhD in computer science, of course in physics, in math, but also with no PhD at all. Because quantum computing is actually opening itself to different types of contributions. And that's why I wanted to show you this stack to see how many layers are there where people can make a difference. People can apply their knowledge to quantum computing. And let's start from the bottom, actually. So at the bottom, we have hardware. So all the hardware providers. These are companies that today are offering access to quantum computers. As you know, there are numerous companies. I will show you later a slide with like a landscape of companies. It's not by any means a complete overview, but I will discuss that later. But you know that there are numerous approaches to achieve quantum computing capabilities for a computer, and we have superconducting qubits, ion traps, photons, annealing. These are all different architectures, different approaches for quantum computers, completely different from each other, with pros and cons in each situation. Me personally, I am not in the business of quantum hardware. I can, of course, I cannot reveal, I cannot reveal secrets about JPMorgan Chase, the bank I work for, but for sure I can easily say that JPMorgan Chase is now working on a new quantum computer. So what we're doing is renting access to quantum computers, as I think many other people in the audience today are also doing. There are companies that offer access to the quantum computers, but going up on the stack, we have the circuit layer. So circuits are basically the inputs that goes into the hardware, and they're built in a language. It's like a low-level language, similar to the assembly language in classical computing. As I will explain later, there is a lot of software engineering that takes place at this layer, the circuit layer, because circuits have to be generated and compiled, or more precisely, they have to be transpiled. I will explain later why I'm using the word transpiler as opposed to the word compiler. Also, this can be like a hardware agnostic form of optimization, but there is also something that can be done once we know the hardware on which the circuit will be executed. So we have hardware specific optimization. I will talk about this later, but this is just to give you an overview. Then at the next layer of the stack above the circuits, we have algorithms. So quantum algorithms are not many. There are not many quantum algorithms. For example, I was thinking about the fact that how many classical algorithms do we have today? So many that it's even impossible to count them. But the quantum algorithms are often known by the names of their inventors. So that also is a sign of how difficult it is to find and to devise a new quantum algorithm. For example, Shor's algorithm, say Grover's algorithm. So these algorithms are known by the name of their inventors. The algorithms, as I will motivate later, are partitioned in algorithmic components like variational forms, optimizers, feature maps, and so on. And as you can see in this layer, I have also included classical algorithms. Why did I do that? The reason is that in this phase of quantum computing, it's called, many people call it the NISQ era, noise intermediate, NISQ, I forget what the S stands for, noise intermediate, I apologize, I don't remember what the S stands for. Of course, the Q stands for quantum. This was a term introduced by John Preskill. Basically, in the NISQ era, where computers have noise.
Marco, I think it's scale, noise intermediate scale quantum.
Intermediate scale, thank you so much, Rui. Yes, noise intermediate scale quantum computers. So the computers don't have many qubits, the computers have noise, the qubits have noise. So in this era, classical algorithms are still capable of doing anything that a quantum algorithm can do. Of course, when a quantum computer becomes bigger, the algorithms that we have implemented today are most likely still exactly going to be applicable to the problems of the future. So for example, like say Grover's algorithm is not an algorithm that works now, and then if we reach quantum advantage or quantum supremacy, Grover's algorithm doesn't work anymore. It will continue to work. So all the algorithms we're working on are going to be applicable to the problems of the future. But as of today, there is nothing that a quantum computer can do that a classical computer cannot do as well. So why don't we take advantage of this limitation of quantum computers to actually introduce in our software stacks classical algorithms that the most important thing is the following, like certain problems can be solved in many different ways. There are numerous different algorithms to solve, for example, for the computation of the ground state molecular energy that I mentioned before when I talked about caffeine. There are many different algorithms that can be used. But what the quantum computer scientists are using in quantum computing is right now the variational quantum eigensolver problem that takes as an input the Hamiltonian simulating the particular molecule of interest, and then computing the smallest eigenvalue of that Hamiltonian, which is a Hermitian matrix. So it has all the eigenvalues are real, and the idea is to compute the minimum of those eigenvalues, and that corresponds to the ground state molecular energy. Instead of the variational quantum eigensolver algorithm, we could use a phase estimation. Take both VQE and phase estimation, take a Hamiltonian as an input. So what I'm saying here about the classical algorithms is that we should have a classical algorithm that takes a Hamiltonian as an input as well. So it's something like that we need to do when we introduce a classical algorithm on the stack. It has to be a classical algorithm that takes exactly the same input as the quantum algorithm. It doesn't solve the problem in a different way. So this basically allows us to swap the quantum algorithm with a classical algorithm during our experiments to generate reference values to contrast and compare the results that we are getting. All the rest remains the same. So in a sense, we have isolated the quantum algorithm in our experiment, and the rest is the same, except of course for the hardware. If we have a classical algorithm, we cannot execute the classical algorithm on a quantum computer. We're going to execute it on a classical computer, but we have isolated the algorithmic layer, and if there is any problem in the other layers, for example, the layer above, which I'm going to describe in a second, we're going to be able to see that. And also we can see the validity of our quantum algorithms if they give us the same results as the ones that we get classically. Then we have domains: finance, optimization, AI, chemistry, and many more. These are domains with exponential problems in them. And in these domains, we have applications for finance, risk analysis, portfolio optimization, option pricing. We have optimization problems like these are like maybe textbook optimization problems here, but there can be many more, like the traveling salesman problem, max cut, and so on. In AI, we have support vector machine, neural networks, reinforcement learning. In chemistry, as I mentioned before, you know, the ground state molecular energy and so on. And going one layer above, we have a layer for interfaces. So how do people get into this stack? There is an interface layer at the top that offers API access, cloud access. I will explain that later. Web access. So you can actually have the whole stack installed on your desktop, except of course for the hardware. and then you will have APIs. Or you can have the APIs hosted on the cloud. Or you can just have a web interface with a UI. And that's what I would like to say. Like, for us, like researchers doing research in quantum computing, especially in algorithms and applications, we want to contribute. We want to contribute code, right? We write an algorithm, we implement it. So we need to have like a programmatic interface. We need to be able to commit code to this software stack. But let's take a domain specific expert. These are the two people that you see on the right here in this slide. Like we have a man at the top who is in this case like a domain expert, like a chemist. And then you have a lady writing algorithms and in the middle. So like you have different people working at different levels. So a person working at the algorithmic level might want to commit algorithmic code. A person working at the domain level, this person, for example, may be a financial analyst. And this person says, for example, like, I don't care about quantum computing at all. I just want the best answer, the most correct answer in the shortest amount of time. I'm very happy to know that there is quantum computing running in the background, but I don't even want to learn quantum computing. I just need to perform a financial optimization type of solution, and I need the best solution. So these people most likely don't even want to be bothered with even writing code. They just maybe want a UI. So that's the type of diversity that quantum computing offers. So another thing I wanted to emphasize is if you see at the bottom, we have a bulleted list. So I just mentioned the usability, but there is also a need in quantum computing for hybrid computing, because here, for example, the top two layers, the API and the domain and application layer, are all classical. They run on a classical computer. The algorithmic layer is also, of course, running on a classical computer because it's generating a circuit, but that's a quantum specific type of execution. And then at the bottom, we have the execution of real hardware. So the generation of the inputs to the quantum algorithms, that's performed by the application layer. The application layer is responsible for taking data, for example, the data of a financial institution, and from that data, creating the input to the quantum algorithms. So that translation layer takes place on a classical computer. And what are the software engineering principles that we are concerned about? We need to continue, as we did in classical computing, to make the code modular, reusable, and extensible. We also have the need for as I mentioned before, the classical algorithms to take the same input as the quantum algorithms. And in this phase of quantum computing, it's also important to, in my opinion, to be able to generate circuits so it's important to be able to build algorithms that are flexible and that can be executed on different computers, different hardwares. Because the quantum computing landscape is changing fast, and there are new vendors that arise constantly. There are many new companies, many vendors that provide quantum computing hardware access. So it's important to have the flexibility to work on a quantum algorithm without having to rewrite that algorithm if one day we change hardware. So that's property. And going back to the hybrid computing property and software engineering principle that I mentioned before, I wanted to mention that it's also important to identify, almost like a compiler would do, identify what are the parts of the problem that can be solved classically, and what components in the algorithm are extremely complex. So it's almost like important to partition a problem into anything that can be done classically should be done classically, and quantum computing should only be used for really like complex operations. So it's almost like a partitioning of the problem into classical and quantum. So this is what I give you here as an example. So let's take chemistry as a domain. We have problems like the ground state molecular energy, dipole moment, and excited states. And here we have an end user, like who is a domain expert. This person is actually interested in this example, which is very simple, in computing the ground state molecular energy, dipole moment, and excited states of hydrogen, the simplest molecule in the universe, 2 atoms of hydrogen. So here we have a configuration of the molecule using one of these classical computational chemistry software packages that you see here. There are many more: Psi4, PySCF, PyQuanti, Gaussian, and so on. So you see, this is all classical computing. What we do at this point, we define the 2 atoms with their own geometrical coordinates, x, y, and z. And the unit of measure is angstroms, and then we let one of these drivers execute some basic computations, like the computation of the 1 and 2 body integrals in molecular orbital basis, and other properties like the dipole integrals and so on. We don't, of course, let these drivers compute the ground state molecular energy, because we want that to be computed by the quantum computer, but we need this input, which actually scales very well. So from here, we can now go to the next phase, which is the generation of a qubit operator, which is basically the Hamiltonian. And what we do at this point is use an algorithm like VQE to generate the circuits that will be executed on the hardware. And the circuit can be optimized. As I mentioned before, there is a compiler, or rather a transpiler, that does this work, so eliminating redundant gates, and so we can compute the ground state molecular energy of hydrogen. If we repeat the same experiments at different interatomic distances between the atoms, you see that we can compute the this graph here, which basically represents the dissociation profile of molecular hydrogen. We can also compute the dipole moments and the excited states, which take place when the electrons move to different orbitals. So this is all possible now with quantum computers, even though only for small molecules. We're not at the point of simulating caffeine, as I mentioned before. But as you can see here, that's where I explained before, we need to be able to separate things that can be computed classically. For example, everything up to the point of generating this qubit operator has been computed classically, and then the Hamiltonian is passed as an input to one of these algorithms to generate the result. This stack that you see at the left is a replica of the stack that I showed you before, except that it is now specific to the problem of chemistry. So in terms of software engineering principles that need to be applied at this point, I listed here a few quantum algorithms that I worked on, that I've worked on. For example, the variational quantum eigensolver, QAOA, Grover, and so on. I wanted to mention that all these algorithms have some shared routines inside. For example, VQE uses variational forms, also called ansatses, and classical optimizers. Grover, Deutsch, Josa, Bernstein, Vasirani, and Simon use oracles. So there is always a need for, in my mind, there is a need for isolating shared components. So when we write quantum algorithms, we have to keep in mind, almost like a demon running in our head, that we may want to reuse certain components in the future, even though we might not be ready to know that. But for example, like when we do Grover, Oracle, the Oracle component should be isolated. And then if we do that, the next time we have another algorithm that uses oracles, we have that component. And then we can, of course, implement that component. We can have different oracles. And if we use this structure, our colleagues, our collaborators can then extend, of course, our components, specialize them, and reuse them in different situations. And the same thing can be true for us. So we avoid the copying and pasting of code. Remember that I mentioned that at the algorithm, at the circuit level, there is a need for a transpiler. So a transpiler is different from a compiler. Compilers are supposed to take a high-level language and translate it into a lower-level language. So, for example, a Java compiler transforms a Java program into bytecode. And then you have a just-in-time compiler that transforms the bytecode into machine-level code. So we have two levels of compilation, but every time you go to a lower level. At the level of circuits, however, the compilation is actually horizontal. So you go from one circuit to another circuit. You make the second circuit more efficient, but it is still a circuit even written in the same language. So that's why it's called the transpiler. And these are called the transpiler passes. So you can have different passes that put together make up the transpiler. So it's very important to optimize circuits, because you can end up having a much better circuit, much more efficient, if you let it go through transpilation. And then you can even have a hardware-specific optimization. So by knowing the architecture of a quantum computer, by knowing the qubit connectivity, by knowing which qubits perform better, you can actually optimize a circuit specifically for that hardware. So this is another important component for those of us who are working at a lower level, like circuit optimization. This is another phase of the quantum computing process and stack, where you actually end up using software engineering principles to optimize the low-level circuits. Remember I mentioned before that I was going to show you like an industrial ecosystem landscape for quantum computing. So if you remember the software stack that I showed you before, software and hardware stack that I showed you before, this is the same stack, but with vendors, with companies. And this, by the way, is by no means complete. And I want to say a disclaimer here, like I may not have included all the companies, I may have forgotten, but some companies may appear at different levels. But I think this is a good overview in my mind, based on what I've seen of companies that are working at different levels. So at the cloud point, we have Amazon and Microsoft. Then we have applications, algorithm, circuits. So I didn't put JPMorgan Chase, the company I work for. because it's like the work we're doing is not shared, it's not public, even though we are committing it to Qiskit, and we're writing papers. But for example, we're working at the level of algorithms, applications, and circuits as well. But you see, this is like growing so fast with new companies, a lot of startups. And at the level of hardware, I wanted to mention that in the quantum domain, there is both the quantum computers and the quantum key distribution solutions, which I will explain in a second. Remember, I mentioned also that it's important, and in this era, in the NISQ era, to be able to move from one hardware device to another. I think it's actually gives us some flexibility to experiment with different computers. So ideally, we should adopt a policy in which we write an algorithm regardless of the underlying computer. And then we can switch from one computer to the other and be able to execute our algorithms on different hardwares. There are some companies that are already providing this type of flexibility. For example, if you allow me to go back to the previous slide, CQC, here it's called the Cambridge Quantum Computing, is a company that gives you this type of flexibility to generate circuits for different hardware providers. And finally, I would like to mention that quantum computing, as we mentioned, doesn't have the ability to solve problems today that are like of industrial scale size, but in the future it will. So some problems that cannot be solved today with a classical computer will be solvable. And among these problems, there is the factorization of large numbers. There is already an algorithm that solves that problem, of course, on a smaller scale, and it's called the Shor's algorithm. But in the future, Shor's algorithm will be able to break today's public key encryption. So algorithms such as RSA and Diffie-Hellman will be broken by Shor's algorithm. Does it mean that we have to wait for quantum computing to make that step and become operational before taking actions, before replacing our cryptographic algorithms with quantum resistant algorithms? The answer is no. We need to do something now. And in fact, many standard organizations and companies and consortiums of companies are working on this because think about this, like there are already attackers that are taking snapshots of private communications between different parties. They're taking those snapshots today. They cannot decrypt the data. So if I send an email encrypted to a colleague or a customer, or if I save some documents in my database, attackers are not able to decrypt the data today, but they will be able to decrypt it 10 years from now, maybe. So 10 years from now, the information that is confidential today may still be confidential. So it's important to start re-encrypting the data and adopting new quantum resistant protocols with new quantum resistant algorithms. And at JPMorgan Chase, my team and I are also working on quantum key distribution, one of the solutions for this problem. I would like to quickly go on part 2. I know we don't have so much time, but this is a very short part because it's just like a thought, like something that I would like to propose to the community working on software engineering and interested in quantum computing as well. I think all of us here in this audience are familiar with static and dynamic code analysis. In particularly, I'm concerned about static analysis. That has been my area of research for many years as well. And static analysis is a beautiful tool and a beautiful technology that allows you to mathematically model a program without executing it. But in order for this analysis to be useful, it has to be precise. It doesn't have to have too many false positives. The reason the false positives arise is because the analysis is often flow insensitive, context insensitive, and path insensitive. So let me explain what this terminology was introduced by Barbara Ryder in this keynote paper that she wrote a few years ago. But let me explain what flow sensitivity means, for example. Here we have an example in which we have a field, x.f, that is confidential because it's coming from the open world. Somebody's reading that field, say like confidential, means it's coming from a protected database. So somebody's reading that field from a database and may contain a credit card number or something like that. Later, this field x.f is overwritten with the empty string. So it's no longer confidential. And then it is disclosed to the world. This means that there is no confidential violation here, no confidentiality violation. But an analysis that is flow insensitive will not be able to realize that the field was overwritten, and in reality will collect both the confidential data and the empty string, and conservatively it will it will report that there is a confidentiality violation. So that's a source of imprecision. Another one is a context insensitivity. So here we have an ID function, the identity function, that returns the same value that was passed as an input. So at the beginning, we have a call to ID, which returns Y1, and then a call to ID that returns Y2, and Y2 is confidential for the same reason as before. So now, an analysis that is context insensitive will mark conservatively the return value of ID as confidential. And for this reason, the third instruction will be reported as a potential problem. And finally, path sensitivity. Here we have two instructions. One is called the x.f equal read, which only happens if B is true. And then we have write of x.f, which only happens if B is false. So these two instructions never happen in the same program. But conservatively, because the analysis is path insensitive and doesn't know the value of B, it will have to model the execution of both statements and report a problem. These are, if you want an analysis to be context sensitive, the analysis becomes exponential. Path sensitive, exponential. Flow sensitive, exponential. So we have three sources of exponentiality right here. And that is what makes static analysis not scalable. Also, let's look at this example. You see that the variable name here is tainted because it comes from the open world. And if we follow the flow, we see that the variable buff, a stream buffer, becomes tainted as well. But fortunately, it looks like we're not in a bad situation because the last instruction is not revealing buff, it's revealing buff 2. So it looks like an analysis could stop here and say this program is safe. In reality, if we look at where buff is coming from, it was instantiated in another method. And that buff variable was passed as both the first and the second parameter to the method foo. So buff2 is also tainted, and this actually makes this a real threat. This is a real security violation. So the analysis has to be context sensitive and has to be also able to go back and analyze different procedures. But this makes the analysis extremely complex. That's why we have this constant dichotomy between scalability and precision. As I mentioned before, if you want the analysis to be precise, it has to be exponential. That's why this is an incredible field of research that has not been explored yet, in which quantum computing can actually make a difference. So if we look at this paper that was written in 2013 at ICSI, why don't the software developers use static analysis tools to find bugs? The answer is too many false positives, but the solution can be quantum computing. And that's it for me today. I'm sorry if I went a little over, and I'm very happy to take a few questions if you guys allow me.
Thank you very much, Marco. It was a really great talk. So I think we have time for some questions. And I think some people joined us a bit later. So I'd just like to mention that we are recording this talks, and also we are recording the discussion session, and we plan to make them available publicly online on the workshop website. So if you have any concerns, please just let us know so that we don't record your part of the. So if there are any questions, you could raise your hand on Zoom, or you could also send us on directly on the Zoom window, or on our channel on Slack. So please just let us know. Okay, so we have one question from Luis Cruz. But Luis, if you want to ask yourself, you can unmute and ask it. It's okay too.
Okay, I can do that. Can you hear me?
Yes.
Yeah. So thanks, Marco, for such a great keynote. It was really interesting to hear all about these different perspectives on quantum computing. And my question is, how much of debugging and testing techniques that we have nowadays for software engineering do you think that could apply for quantum computing as well?
Thank you very much, Luis. Yes, I agree with you. They can be applied. So, of course, all the tools that I use today, static analysis, dynamic analysis, testing, they can be applied no problem to all the levels of the software stack that I showed you before. Absolutely. It's an incredible loop in the sense that static analysis, debugging tools can be very useful to us as quantum computing researchers and developers. But quantum computing itself can help us, as I mentioned in the second part of our presentation, for anything that is not scalable. And so it goes back and forth. It's a very interesting property that we are looking at right now.
Thanks.
So any other questions for Marco?
Yes, may I?
Yes, please go ahead.
Thank you. Yes, I would also like to stress it was a great keynote. I enjoyed it quite a lot. Marco, so my question is maybe more towards, let's say, the long term, I don't know. But my feeling is that these days, at least, I mean, and considering classical computing, there are lots of things that I can do as a researcher, which is what I am, let's say to explore the computing power that, let's say, my laptop has. And I will give a concrete example. I can, for example, I don't know, install specific hardware, or I can actually access drivers to estimate the energy that my laptop is consuming and things like that. And that is quite interesting for me, and it opens up many directions for research and for actually knowing myself better what my computing machine does. And the current scenario clearly within quantum computing seems to be that only the major players like IBM and Google and D-Wave and Honeywell and so on do have access or have enough money to build or to use at least, let's say, freely in the sense that they are always available, quantum computers, so to say. And my question is, do you envision, can you even roughly estimate how long do you think it will take, or if it will happen at any moment, that we will have more, let's say, democratic access to quantum machine? We as let's say ordinary people will have access to quantum machines somehow.
Yeah, so I think several companies are already offering this type of free access. IBM, for example, but I also think other companies are. I heard maybe Amazon and Microsoft, like Amazon and Microsoft do not have a quantum computer as far as I know, but they offer cloud access to other quantum computers, and at a certain point I think some of this access is actually even free. So for small computers, then if you go to bigger computers, it becomes like you have to pay for that. But I think there will be a point in which, yes, like access to small computers is continue to be given for free maybe, and that's actually something that is very helpful for us at this stage to build our initial algorithms. We even our, not necessarily initial algorithms, but our algorithms. Then of course we cannot test them on big data, but we can definitely devise these algorithms, test them on simulators and also on these computers. I'm also interested in what you mentioned, Joao, about accessibility to the tools, to the the data that the computer collects, so that you can actually look at like the time that it took, you know, how many qubits were involved, and log files and so on. So it's very important to get that information when you execute programs. So for example, when we write a paper now in my team at JPMorgan Chase, we're always collecting as much data as we can from the hardware providers, so that we can always go back later and say, like, how much time did it take again when we ran that experiment, so we don't have to rerun it again, and we can collect data and report it in our papers.
Okay, great. Thank you for the answer.
Yes, so I see that Mohammed has raised his hand. So Mohammed, please go ahead.
Thank you, Shaukat. Can you hear me?
Yes.
Okay, so my question is a follow-up to the question Louise asked. Maybe also it relates to the previous question. You said quantum algorithms potentially provide solutions to program analysis problems, but that requires access to powerful simulators or computers to analyze them, right? And for some time to go, we will be analyzing quantum programs on normal computers and normal simulators. So I guess for the time being, it's more of a challenge to analyze complex quantum programs on normal computers, isn't it?
Yes, so basically I was also talking about analyzing non-quantum programs. For example, web applications. Web applications are gigantic, you know, like millions of lines of code. So, for example, banks have the web applications internally and externally with millions of lines of code. Similar, like insurance companies, universities have this type of application. So I was not talking about necessarily analyzing quantum programs with program analysis, but in general, analyzing classical programs with static analysis. Right now, we are not capable to analyze, no static analyzer exists that can actually, in a sense, digest a very large program, producing sound results without too many false positives. The problem is exponential in the size of the program being analyzed, and so the static analyzer just cannot do it. And so that's where you have analyzers taking approximations which generate false positives, or excluding parts of the program under analysis from the analysis itself, which generates false negatives. So we need to, in the future, we can even start now building algorithms for quantum computing that analyze classical programs. And we cannot, of course, like today, have the scalability that allows us to analyze a program with, say, 2 million lines of code, but we can start building an analyzer that analyzes a small program, and then the algorithm will be reused as the quantum computer grows in power. It will be reused later with more power, and as the quantum computer becomes powerful enough, we will be able to analyze larger programs as well. I hope I answer your question, Mohammed.
Yes, my question is also about the other way around. So if you want to use classical algorithms and computers to analyze quantum programs, I think that is a very difficult problem, isn't it?
Exactly. It's I think it is difficult because quantum programs can be also very large. When you say quantum program, do you mean at which level? You mean like maybe a circuit?
I mean, it starts from there, but it could be also more complex protocols as well, right?
Yes, exactly. Yes. So and the problem is also that because the stack involves hybrid computing, then you have to be able to analyze even different languages and the different components. Absolutely. So we have a need for that as well. I completely agree with you. We need to be able to have tools that allow us to validate quantum programs as well.
Thank you.
So we have some comment from Carlos. Please go ahead.
Sorry, just looking for my unmute button. No, everything I wanted to say is in the comment I put to everyone, which is just to add to what Marco was saying. As I myself am a researcher in quantum computing rather than software engineering, I don't think that anybody in the field is thinking that quantum computers will be in the home anytime soon. But cloud quantum computing, and in particular secure cloud quantum computing, that's the ability of a client to perform computations in the cloud without divulging those computations to the cloud. So the next best thing basically to having the quantum computer in your own home are active research areas. And I linked a review paper to that research field in the chat box if anybody is interested.
Yes, it makes perfect sense. You're right, Carlos. I completely agree with you.
Carlos, I have also added your comment to the Slack channel, just for the record.
All right, so I think with this, we would like to thank Marco for a very interesting keynote. And I think we are a little bit late in the time, but I think we can still take about 10 minutes break because we still have a little bit buffer at the end of the workshop. So I think it would be okay to restart about 3:41, 3:42, something like this. So thank you so much, Marco, for your
Thank you, Shafat,
really appreciate.
Thank you both, Shafat,
Thank you,
for the invitation and for this great opportunity. And as I said before, I hope we can see each other in person soon, next year.
Hopefully, for sure. Okay, take care.